Okay, let's jump right in. We're looking at the paper JustRL, scaling a 1.5B LLM with a simple RL recipe,
And this one tackles a huge question in the field right now, especially for smaller models.
which is all this crazy complexity we see in training pipelines, multi-stage training, dynamic hyperparameters. Is any of it actually necessary?
Or is it maybe even counterproductive? The authors here propose the opposite. They call it JustRL, and it's a super minimal approach. Single stage training, fixed hyperparameters, that's it.
And the results are, frankly, stunning. They hit state-of-the-art performance on 9 different math benchmarks.
But the real kicker is how they got there. They use 2 times less compute than more complicated methods like ProRL v2 and Questa.
2 times less. And the training itself was exceptionally stable. We're talking smooth, steady improvement, none of the collapses or plateaus that usually justify all that complex engineering.
And this is my favorite part. They're ablation studies where they tried adding back some of those standard tricks like length penalties.
It actually made performance worse?
Exactly. It crushed the model's ability to explore. So our mission today is to unpack how taking things away, how simplicity became the new state of the art.
So let's start at the beginning. Why even use RL for these small language models in the first place? Why not just stick with supervised fine-tuning?
It really comes down to a hard ceiling on performance. Supervised fine-tuning, or SFT, is where you're basically distilling knowledge from a big teacher model into a smaller one.
It's stable, it's efficient, it's what most people do to get an SLM out the door.
Right. But the small model can never get better than the teacher model. You're fundamentally capped by the quality of the data it was trained on.
You can't learn a solution that teacher never showed you.
Precisely. And once you hit that saturation point, more data doesn't help. RL is the only way to push past that limit. It lets the model explore and find new, sometimes better, ways of reasoning that weren't in the original data set.
But that exploration, that power, came at a really high price.
Correct.
Instability.
Oh, huge instability. I mean, for the last year or so, RL for SLMs has been notoriously difficult to tame, and that's what led to this arms race of complexity.
An arms race is a good way to put it. Everyone started throwing more and more sophisticated techniques at the problem just to keep it stable.
Yeah, you saw all these interventions pop up. Things like multi-stage training.
Right, like Deep Scaler.
Mm-hmm.
That was what, a 3-stage pipeline?
3 stages, yeah. They'd gradually increase the context lengths from 8K to 16K, then all the way up to 24K, just to ease the model into longer reasoning.
And FastCaro was even more complex, like 5 stages alternating between compressing and extending the chain of thought, different batch sizes for each phase.
It's a massive engineering headache. You're managing all these moving parts.
Then you have methods like ProRL v2 trying to manage the output itself. They had an 8-stage pipeline with scheduled cosine length penalties.
Yeah, meticulously trying to control for every possible failure mode at once.
And we can't forget Questa, which even changed the input data itself with curriculum learning, feeding the model partial solutions as hints.
All of which came from bigger, more powerful models. So, the complexity just keeps compounding.
Which brings us back to the core question of this paper. Is all of that complexity a real benefit, or are we just solving problems that we created with other complex choices in the first place?
It really feels like that, doesn't it? It's like you add one fix, like KL regularization, and suddenly that fix introduces a new instability which requires another fix, and on and on.
Okay, so let's dig into the JustRL recipe itself. If they threw out that whole multi-stage dynamic circus, what did they actually do?
Well, the most important part of the paper is the list of things they didn't do. Their entire approach was about sticking to the absolute basics of RL and seeing if those fundamentals could hold up at scale.
So what's in this minimal setup?
Okay, so the algorithm is just the default GRPO in the VRL framework. The reward is simple binary. You're either right or you're wrong. And the verifier is a lightweight, rule-based one from DAPO.
Let's pause on that verifier for a second. Why is that specific choice a big deal?
It's a huge deal for compute. A lot of systems use heavy symbolic math libraries like SIMPy to, fully parse and evaluate every algebraic step.
Which is very accurate, but slow.
Extremely slow, especially when you're doing thousands of rollouts. The DAPO verifier just uses simpler string matching. It's a bet that you can get good enough verification without that massive computational overhead.
So they're prioritizing training speed over perfect verification at every step. What about the training structure?
Single stage. This is the big one. One continuous run from start to finish. And critically, the hyperparameters are fixed for the entire run.
Fixed. So no adaptive temperature, no changing the batch size.
And crucially, no mid-training KL reference resets.
Okay, explain that for people who aren't in the weeds. A KL reset is basically a safety valve, right?
It is, yeah. It's a trick to stop the model from drifting too far from its original SFT baseline. If the model starts outputting garbage, you can sort of reset its leash and pull it back to a known good state. JustRL just didn't need it.
Now, they did use one technique they call clip higher. What's that about?
It's a standard stability feature in GRPO. It just puts a cap on how much the policy can change in a single update. It prevents huge catastrophic steps, which is really important for long, complex tasks like math. They see it as part of the baseline, not an extra trick.
Got it. And the most convincing part might be that they use the exact same fixed setup, same learning rate, same temperature on two totally different foundation models.
Right, on DeepSeek and Nematron. Without any special tuning for either one, that tells you they found something genuinely robust, not just a lucky set of numbers for one specific model.
And they didn't even use an explicit length penalty, just a max context length.
Yeah, and that decision to not explicitly penalize length turns out to be one of the most important ones they made.
All right, let's get to the evidence. They started with the DeepSeek backbone, which was the weaker of the two models. How did it do?
This is takeaway number one. A decisive win for simplicity. The JustRL model hit 54.87% average accuracy across 9 benchmarks. That beat the super complex ProRL v2, which only got to 53.08%.
So it performed better. But what about the cost? That's the real headline for anyone paying the bills.
The cost difference is just staggering. JustRL used about 1.4 times 10 to the 8th K token budget.
Okay.
ProRL v2 used double that. 2.8 times 10 to the 8th. So JustRL got better results with literally half the compute.
Half the compute. That's incredible.
And if you compare it to another method, BroRL, which tried to win with brute force by using 512 rollouts, it used almost 5 times more compute than JustRL.
And the proof of stability is right there in the training graph. It's just this smooth, steady line climbing from around 28% up to 58%. No drama.
Exactly. It's the perfect visual argument against needing multi-stage pipelines. You build those pipelines to handle the exact collapses and plateaus that JustRL just never experienced.
Okay, so that was on the weaker model. What happened when they moved to the stronger base, the OpenMath Nematron model? Did the simple recipe still work?
It absolutely did. And this is takeaway 2. The approach is robust. They used the identical fixed recipe and achieved 64.32% accuracy, which just edged out Quest A at 63.81%.
That's a really tight margin. It sounds like both methods are pushing the absolute limits of a 1.5B model.
They are, but look at how they got there. The contrast is night and day.
Right. Quest A is that incredibly complex curriculum learning approach we talked about.
Yeah.
They had to create hints for the model using partial solutions.
Yeah, which means you need a whole separate data pipeline with a larger teacher model just to generate your training data. It's a massive upfront cost.
Whereas JustNRL just used standard question and answer pairs.
Exactly. And the compute savings are still there. Quest A needed about 2.4 times more compute budget than JustNRL did on the Nematron model.
So even when the performance is neck and neck, the efficiency isn't even close.
Not at all. And the fact that this same simple, untuned recipe works so well on 2 completely different model architectures, that proves this isn't a fluke. It's a genuinely stable baseline.
Okay, so let's get into the why. The paper does a great job analyzing the training dynamics, and this really feels like the core intellectual contribution here.
I agree. The plots they show are probably the most damning evidence against adding unnecessary complexity. Let's start with policy entropy.
Right, which is basically a measure of how much the model is exploring.
Exactly. And in their runs, the entropy just naturally bounces around in this really healthy range between 1.0 and 1.6. It doesn't drift off into space and it doesn't collapse.
If it collapses, the model gets stuck in a rut. If it drifts too high, it's just outputting random nonsense.
Right. And this stable entropy is why they never needed those KL reference resets. The system was in balance, so it never needed that emergency brake.
And the mean reward curve shows the same thing. Just a smooth, steady climb from negative 0.6 up to positive 0.4.
No long plateaus, no sudden crashes. It was just constantly learning, which is why they didn't need multiple stages to, kick it out of a rut. It never got into one.
But what about the response lengths? This is a huge problem in other methods. Models get super verbose and hit the context limit.
Yeah, and that's why everyone uses explicit length penalties. But look at the data here. The model starts out verbose, averaging around 8,000 tokens.
Okay.
But then, with no penalty at all, it naturally compresses its own outputs down to a stable 4,000 to 5,000 tokens and just stays there.
Wait, so the model just figured out on its own that being overly wordy wasn't helping it get the right answer?
That's exactly it. The implicit reward for just being correct was enough of an incentive to be concise. The explicit penalty was completely redundant.
Wow.
And that leads to the most fascinating part of the paper, the destructive ablations. They put 2 of these standard tricks back in, and the whole system just broke.
Okay, so what happened when they added that explicit penalty for being too long?
Performance immediately tanked. It plateaued at 50% accuracy, which is a full 5% drop from their baseline.
But why? If the model was already getting shorter on its own, why would penalizing long answers hurt it? It seems so logical.
Because it created a conflicting goal. The pressure to be short was so strong that it completely collapsed exploration. You can see it in the entropy plot. It dives down to 0.5. The model basically got scared to think for too long.
So if a hard problem actually needed 6,000 tokens of careful reasoning, the model would just give up at 3,000 to avoid the penalty, even if it meant getting the answer wrong.
Precisely. The added complexity, the penalty, destroyed the delicate balance the simple baseline had created. It made the model prioritize length over correctness.
And it got even worse when they added a more robust verifier on top of that. Performance dropped again, down to 45%.
Which is so counterintuitive, you'd think a better verifier would help. But they think the original, stricter, rule-based verifier was creating a useful kind of pressure. It forced the model to be extremely precise internally because it knew only a perfect answer would get rewarded. When the verifier gets too forgiving, that incentive is lost.
This is the real lesson for anyone building these things. These standard tricks are not magic. The complexity that fixes a problem in one system can completely break the stability of another. You have to validate everything empirically.
So when you put it all together, what does this paper really tell us about where RL for these models is heading?
It feels like a really strong methodological argument. It shows that stable fundamentals, applied at the right scale, can beat these super complex multi-stage methods. And it can do it while using way, way less compute.
Yeah, up to 5 times less in some cases. It's a call to action for researchers. Stop defaulting to complexity. Start with the simplest possible baseline, make sure it's stable, and then only add a new component if you can identify a specific failure that component is guaranteed to fix.
Right. Don't add a trick just because you saw it in another paper. Your system might not even have the problem that trick was designed to solve.
We should probably mention the limitations, just to be fair. These results are for 1.5B models doing math. We don't know for sure if this simple approach will scale to, say, a 70B model or a totally different task like code generation.
True, and they can't say for sure which simple part was the most important. It's probably the combination of all of them working together. But they've definitely proven that simple, scaled RL is a strategy we've been overlooking.
Yeah. You look at the results and you just think of that Antoine de Saint-Exupéry quote they used. Perfection is achieved not when there is nothing more to add, but when there is nothing left to take away.
It really makes you wonder if the field has just been treating symptoms created by its own complexity. This paper is a chance to reset. It forces you to ask, if they got better performance using half the compute by removing things, what could you take out of your own pipelines?